Approve.
So, other lecture completed. Let's bring the computer.
Yeah.
So sit down.
Okay. Thank
No, I mean I was just joking. I mean I hope you didn't forget it in the lecture room. Again, I mean, since you missed it at the end of our lecture. No, okay, fine. No, fix it. So you had some questions.
Yeah.
Mm-hmm.
Because the last several days I was busy reviewing slides. Yeah, and I came across some questions.
Okay.
Actually, I had already made some discussions with the classmates, but I still have.
Okay.
Some
Yeah. Fine. Yeah.
Sorry, wait a moment.
No, that's okay.
We can use this screen. Yeah. Well, I actually about this I don't know why. Did you ask this question? And in my opinion, I think this function is not convex. It's not convex. Well.
Let's agree that it's not about opinions.
Yeah.
It either is or it isn't, right? So the question is, suppose we allow the value minus infinity for an extended ring function. Can such a function be convex? The answer is yes. If it's identical minus infinity, then its epigraph is the full space, which is a convex set. End of story. Okay, a bit more involved. Suppose we allow for the value minus infinity, but also another value. So it's not identical minus infinity. Can that function still be convex? That's the question I'm addressing here, and it's sort of developing the students' intuition for convex functions a bit more general than they are typically used to. So let's be concrete. Suppose that I have the value minus infinity for some arguments and 0 for other values. Can it still be a convex function?
You say. Sorry. Can you say again?
Okay. Suppose I have this function v, which is generic, and I now am thinking about. Okay. Suppose I would allow the value minus infinity for this recourse cost or penalty cost function v, which I do not like because it's the wrong interpretation, because it would be an infinite reward, whereas I'm trying to model penalties. But still, I could think about this as a mathematical object. Suppose I allow this value minus infinity. We already found, yes, it can still be convex, for example, if it is identical minus infinity. But that's not a very useful function for our purposes, right?
Yeah.
So now I make the next step and I say, okay, let's try to think of another example. Again, such a function v, where I do have minus infinity, but also another value. And I just pick 0, but it could be anything else. Try to make this picture in your mind. And the question then is, can such a function be convex? The answer is no. And again, the way to see it is to say, okay, let's look what the epigraph looks like. And that's not a convex set. So that's the point. By the way, this is just a side remark. It's not, say, the key idea behind everything we do here. It's just thinking about, okay, is it reasonable to guarantee that we wish to have a finite valued recourse cost function v? And yes, we have good reasons to do so. In particular, for this side of the story, this value minus infinity, we really wish to avoid for several reasons. The other side of the medal, the value plus infinity, it's a different story, because at least from the interpretation point of view, it's quite thinkable that there are infeasibilities which we simply cannot correct given the available means. And in terms of such a value function of a linear program, that would indeed then be an infeasible problem for that particular right-hand side C, meaning that its corresponding value is plus infinity. That's one part of the story. The other part is, still, I don't like to work with the value plus infinity either. If I can avoid it for algorithmic reasons, for theoretical reasons, let's do so. So let's assume that indeed we have this notion, complete recourse. That's yeah. By the way, what is your background? What bachelor did you complete?
Mathematics.
Okay.
Yeah.
Okay.
Yeah, but actually after graduation, I did management for 2 years in China.
Okay, so
Yeah.
that's a bit rusty.
And then came here, I choose econometrics.
Yeah.
Yeah.
Okay.
Yeah, but actually, I can follow something related to mathematics, but actually, what a pity that my listening is not very good. So sometimes I have to review slides and ask some questions.
Yeah, that's fine.
To further what I listened to.
Yeah, to put it into perspective. And yeah, sure. Yeah. Okay.
Well.
Yeah, the example.
Yeah. So this is not completed, right?
That's right.
Yeah.
The reason, of course, is that we can only
the first this.
Yeah.
Not including
right.
other three parts, right?
Yeah, add a negative orphan, for instance.
Yeah. Oh, yeah. Oh, yes. Oh, well, actually, I don't know why this part could imply to this part.
Oh, it's just I defined V to be the value function of this problem. So instead of writing V, I write that problem with corresponding optimal value. That's the only thing I do.
So just a definition.
Yeah.
Not
nothing happened.
Oh.
Yeah.
So we define this part equal to this part.
Yes. V by definition is the value function of that second linear program. Where the argument of V appears in the right hand side. So instead of writing V of h minus tx, I write the full minimization problem.
Well, actually, about this, I spend a lot of time in finding out why this part could imply to this part. Okay.
It's just a definition.
Okay. Yeah. Well, what about this? I don't know why this part could imply to this part. Actually, I think the minimal symbol is missing there, right?
No, because I have there a closed form formulation for the optimal value. V is defined as this minimization problem.
Yeah.
And I claim that for any argument z, which is scalar,
Yeah.
this is the optimal value under this assumption. What does it say? It says, given any z,
Yeah.
if it's positive,
Yeah.
then it's this coefficient q plus times the positive part.
Yeah.
If it's negative, then it's this coefficient times the negative part. And if it's 0, nothing happens. Okay. Why is that true? Well, because we actually proved that under this assumption,
Yeah.
actually the this function is convex.
Yeah.
So it has a minimum, and it is indeed corresponding to the optimal value of this problem, which we actually... Oh, here's the proof.
Yeah.
And what happens if you do not satisfy this condition? Well, then it pays to say, well, instead of making this equal to the positive part and that to the negative part, I can add a positive amount to both and still satisfy the constraint. And if this assumption is not satisfied, then actually I'm adding something at a negative cost, and since I'm minimizing, I can keep increasing that. So this condition is really necessary to have the equivalence between this minimization optimal value and this closed form. That is some shekels.
Sorry. Actually, now I don't understand why. This is the first part.
That's the first line is the definition, huh?
Is definition. Yeah. I know.
Yeah. Okay.
I know. Yeah.
Mhm.
And actually, I don't know why this definition could imply this.
Okay, so let's consider the ingredients of that optimization problem, which is a linear program.
Yeah.
It says, for a given z,
Yeah.
find a combination of those two decision variables, y plus and y minus,
Yeah.
such that this linear objective is minimized.
Yeah.
That's what it says.
Yeah.
Okay. And now I claim that this is a trivial problem.
Yeah.
For which I can easily read what the optimal value is.
What is trivial problem?
Because this is a scalar problem.
Yeah.
Where there's a single constraint.
Yeah.
Okay, let's first make it even simpler, even more trivial. I know trivial is a dangerous word. Suppose both q plus and q minus are positive.
Yeah.
Do you then
You said this.
Yeah.
This is positive.
No, q plus, the cost coefficient. Y is a variable to be decided on.
Yeah.
You need to find an optimal solution.
Yeah.
Okay. Q plus, suppose it's strictly positive, and also Q minus is strictly positive. It means that for both Y plus and Y minus, I need to pay. Right? And since I want to minimize, less is better.
Yeah. You say this Q plus and Q minus are both positive.
Yeah.
Yeah. Yeah.
No, I'm making it easier by making that additional.
Okay.
In fact, we can relax it to this one.
Okay.
Okay. And my question to you is, if we make that additional assumption that both are positive, instead of just the sum, both are positive, we then agree that this is indeed trivially found as the optimal value. I'm given an arbitrary z, and I need to make that z by a choice of two decision variables, y plus and y minus. Both are non-negative. And then I claim the solution is consider that z and make y plus equal to the positive part and make y minus equal to the negative part. That's optimal. Why is that true? Well, under the assumption that each variable comes with positive cost, as we're assuming now, this is the best I can do, because what could I do otherwise? Well, of course, I'm bound by the constraint. So if, for example, I do not, let's suppose that z is positive, then I claim that the optimal solution is that y plus is equal to z, namely the positive part. What else could I do? Well, I could say, no, I'm going to add a little bit. Instead of choosing it z, I take it z plus 1 for all I care. Then, of course, I need to also make y minus equal to 1, since the difference still needs to be the same as z. But now we look here and see, well, that's more expensive, because I increased y plus at a cost which is strictly positive, and I increased y minus. That's definitely worse. So that's non-optimal. What else could I do? I could try to see, can I decrease y plus? The answer is no. I have to choose it at least equal to the positive part of z. Same story the other way around if z is negative. Okay.
Oh.
And now, the next step, and well, we looked at it from various sides. I can relax this assumption of both components to be positive, both cost components to be positive, to the sum of them has to be positive. And the explanation is actually right here.
Yeah. Yeah.
So that's the full story then.
Yeah.
Yeah?
Yeah.
Okay.
Oh, well.
You actually have a touchscreen. That's nice.
Yeah.
Okay. So it's a mix between a laptop and wonderful.
Yeah.
Okay.
Because I think maybe this is easier for me to use.
Yeah, it's very convenient. Yeah. Oh, now I see it's a ThinkPad. I used to have one of those. The very old model. But it lasted me for almost 10 years or so.
Oh.
Very good. Very good. Okay, so back to, yeah.
Yeah. Oh. Oh, yes. Oh, yes. Oh, yeah. Actually, in slides, I can see a lot of this symbol used a lot of times.
This wiggle, yeah.
But well, actually, I'm not sure what this symbol means.
It means a lot of things. And
A lot of
depending on the context, it may be different. So in this context, it means the slope of h is related to the distribution function f.
It's
It's
related to.
Yeah. It behaves like. And that's actually the context of the content of what much that's following. That actually that we observe, we find this nice closed form formula where we see indeed it's the integral of the distribution function. So that immediately tells us, yeah, sure, the slope of that integral, well, that's of course the function value of the integrand at the boundary. That's all I'm saying here.
Oh.
Yeah.
Okay.
But you're absolutely right. My use of this symbol, it's overloaded because in a different context it may be any type of relational symbol, can be equality or weak inequalities of either type. Sometimes it means is distributed like. So I could easily write, oh, here it is. Omega wiggle f is my shorthand notation for omega follows the distribution as given by the distribution function. You're absolutely right.
I sometimes this symbol means equivalent.
It has many meanings. It depends on the context.
Context.
Yeah. Yeah.
Oh, well, I don't know why this part implied to this part.
Okay, I have here an integral
Yeah.
which reads minus infinity up to, what is it, t?
Yeah.
dfs.
Yeah.
And I say that's f of t.
Yeah.
Agree?
Yes.
Okay. And then I say, okay, I plug in f of t, and I have this outer integral. And that's then what it means.
No. Actually, well, yes, actually, this.
Yeah.
This part implies to this part, not between these.
Ah, okay.
Ah.
So this is about changing the order of integration.
Yeah.
Yeah. This, I mean, so far so good. This is the definition.
Yeah.
And here I say, okay, this integrand I do not like that much because it involves this negative part, and it's very easy to see what it implies. Namely, for any argument larger than x,
Yeah.
then this is 0. So I could as well write
Yeah.
up to x,
Yeah. I know.
and then of course I have this linear expression. And then I do a silly trick. I say, okay, that difference of x and s is just an integral.
Yeah.
Okay, I plug it in. Why would I do that?
Yeah.
Because if I change the order of integration, and that's what I explain here,
Yeah.
then the inner integral becomes this nice distribution function. And I find what I'm after, namely this nice expression for h as an integral of the distribution function.
Actually, I don't understand what this thing means.
Okay, what happens here?
Yeah.
We have a repeated integral.
Yeah.
Outer integral with respect to the variable s, the inner with respect to t. And for a given s, the boundaries for t, the interval of integration, depends on s and the given x.
Yeah.
Okay, so what it actually tells me is there's an area
Yeah.
described by those two integrals over which I need to integrate. And it's this area for, okay, as it's given here, it says, okay, for a fixed s, which needs to be all the way up to x, I can pick, let's say, this one here. Then,
Maybe this one, right?
whatever.
This is x, right?
No,
This one.
no. X is a constant.
Oh.
My variables are s on this axis and t on that axis.
Oh. Yeah.
Yeah?
Yeah.
Okay. For a fixed s, picked on the horizontal axis, no larger than x, anything below goes, so let's say the blue line.
Yeah.
There. Then for that fixed s, my t variable, so on the vertical axis, runs from s up to x. So x is over there. So I start at t, and this is the diagonal line, so t equal s. So it runs from there to there. And I need to do that for all possible s, and that describes then my area of integration.
Oh.
And now I say, okay, but I could, instead of looking, say, at vertical lines, I can also describe this area by horizontal lines. That is, instead of fixing s and then looking how t runs, I do exactly the opposite. I fix t and see how s runs. Well, that's this story. Indeed, I have to pick t between, let me see, here, between minus infinity and x, that I read from the picture, and then I see that s for such a t runs from minus infinity up to t. That's the red arrow here. And I do that for every t, and that also describes my area. Okay, they are equivalent descriptions of the same thing. And the benefit is that the inner integral is now really nice.
Oh.
So that's the trick. Yeah?
Okay. Sorry, I can't recognize this word.
The tail. So
Tail. Oh, tail.
Yeah.
Oh, okay,
Yeah.
okay.
Yeah.
So this is
find, yeah?
oh, sorry.
Yeah, my handwriting. Yeah.
Because I'm not familiar with English handwriting.
No, I can imagine. Yeah. Yeah.
But actually, one of my classmates said your handwriting was very readable. But for me, I'm new here.
Of course, I fully understand. It's okay to ask. That's fine. Yeah.
Yes. Actually, I don't understand what happened in this part.
Okay. Okay. So, given the context that we're working in, I step aside and say, okay, I want to talk about subdifferentiability of convex functions.
Yeah.
So instead of just discussing the function h, I make it more general. I take a function phi on Rn, which is by assumption convex and finite. And that, of course, is the same setting that we're looking here in dimension 1. And I use the result from convex analysis, which tells us that such a function not necessarily is differentiable, but it is subdifferentiable.
Oh.
And here on the slide I explain what the relation is. And indeed, if the function is differentiable, that translates to this picture. We can calculate the slope of the function and the corresponding linear function, which is sharp at that point. That's a supporting hyperplane, tangent plane, if you like. That's then uniquely determined, namely its slope is determined by the unique gradient. And then if you proceed, then you will find that idea of a, okay, I can do this, right? Ah, it works. Wonderful. Now I say, okay, let's consider much the same thing, namely a function which we know to be convex and finite, however, it's not differentiable. Can we play the same trick? Can we always find such a linear minorant with a slope that is corresponding to, well, a generalized notion of the slope of that function? And the answer is yes. Again, given that the function is indeed convex, we can find a linear minorant, which is sharp at the point that we consider. And that's described here. That's it.
Oh, okay.
And today we discussed
Yeah.
how that is useful.
Yeah. Yeah.
Yeah.
So this is also means is a relay.
Yeah.
Okay.
It is. Here it means something like it depends on the Rico structure. Because if I plug in any combination of Q and W, I get a specific function.
Okay.
Yeah? Okay.
Yeah. Well, I don't know what happened. This.
Okay. Forget about it because it's not that important. The issue I'm raising here is that we're indeed here looking at this notion of sufficiently expensive recourse by using weak LP duality, which only tells us that this dual problem, its optimal value, is a lower bound for the optimal value of the primal problem. And the primal is what we're actually dealing with. That's the value function V. Okay. So if this condition, feasibility of the dual feasible set, if that is not satisfied, then we are actually allowing for the lower bound, the value minus infinity. But that doesn't quite imply that the primal also takes on the value minus infinity. We only know it's at least equal to minus infinity. Yeah, well, that's not saying much. And LP theory, duality theory, tells us, well, actually the primal and the dual have the same value unless both are infeasible. Okay, what does it happen? What does it mean if the primal problem is infeasible? Well, it's a minimization problem. If it's infeasible, it takes on the value plus infinity. So in that setting, we can actually have such a value function V, which is either minus infinity or plus infinity. Completely useless, of course. We can't use it to model any realistic problem. It's just an aside, and I include that kind of ideas because I want to sharpen your intuition, your knowledge of value functions of linear programming, because we use it all the time, and the more you know, the better everything falls into place. That's why I'm also discussing this kind of asides, but it's not crucial for the main line of the story.
Okay. Yes. Well, about this, well, actually, this we say no, because we can't, because we can always find possible recourse action. Yes, no, yeah, this part for this part, and but why? Actually, this definition, in my opinion, is the same as this.
No, I can see that why you might think that, but it's not true. And the difference is here.
Yeah.
Here I say for arbitrary z,
Yeah.
anything goes.
Yeah.
Here I say no, I'm only looking at z which are actually depending on omega and x, and then I consider only decision variables x which are feasible and realizations omega which are in the support.
Oh.
And that's of course not everything. Just to give a very simple example, here I say I can only consider non-negative decisions x. But here I allow any z, so for instance also those that are given as these expressions in terms of a negative x.
Also here,
here I restrict to only those vectors z which may actually arise, because I have a feasible first stage decision x combined with a possible realization of omega, and then look at this h omega minus t omega x.
Oh.
Yeah, so that's why it's indeed called relatively complete, because it's relative with respect to the support of the random variables and the first stage feasible set. Whereas complete recourse refers to anything.
Oh.
Yeah.
Okay.
Okay.
Oh, that this word means
Yeah.
RHS.
Yes, right hand side.
Ah.
Yeah, this is something that will come up later when we discuss the exercises.
Oh.
Because it's part of one of the exercises.
Oh.
Yeah.
Oh, okay. Yeah. How do we get these values?
Okay. This is the definition of the problem I consider, and of course, well, almost of course, it's a simple recourse problem. I write this dual.
Yeah.
And then I have these simple bounds on the two variables.
Yeah.
So that's a box in R2.
Oh, yeah.
Oh, those are the vertices of the box.
Oh.
Okay.
Yeah. Yes.
Mm-hmm.
Oh, okay. Thank you.
Yeah.
Yeah.
Okay, you're welcome. Indeed, you're very welcome. Next time, I think it would be more efficient if somehow you could. We spend now a lot of time on searching where your questions are. If you could just make that quicker, then we can spend more time on discussing.
Yeah.
And that's better for you and for me.
Oh, okay.
Yeah.
Okay. Okay.
By all means, you're very welcome.
Thank you very much.
This is good. Yeah.
Oh, well,
okay.
Well, about this. I should know everything in this.
No, but you need to say.
But this is just a reference.
Yeah, it's reference. Then again, I expect that you are fluent in this calculus to do simple things as we do during lectures. For example.
How about later?
No, later appendices. That's just for reference.
Oh.
But the one on that positive part, negative part calculus, I mean, it's trivial.
Oh, okay.
But no, those others are just for reference.
Okay, because before I didn't learn something anything about convex analysis.
Same is true for the students that complete the bachelor year. They know a little bit, but not that much.
Okay.
And what I do is more, and by now it should be obvious that we actually need it, this convex analysis stuff, because that's sort of the key to everything that we do. But no, I mean, I don't expect that you, say, have a deeper background in convex analysis than anything that we cover as we need it. For example, in the exam, I will not ask questions about convex analysis outside the context of what it is that we're talking about.
Okay, so you will always focus on slides.
Not necessarily. I mean, in the lecture notes, there's more than the appendices.
Yeah.
For example, of course, during the lectures, I follow mostly what is in the lecture notes. Sometimes I take a different perspective, being a little bit less formal, trying to develop your intuition and so on. Which doesn't mean that what is in the lecture notes isn't relevant. Then again, the purpose of the goal of the course is that you learn about stochastic programming and its limitations and its power and so on. Not on its own about the technical details, only in as far as they are relevant for understanding what it is that we're doing. And to be honest, that's quite a bit. We need to look at the details because otherwise we won't get anywhere. Well, to you as a mathematician, that should sound familiar.
Okay.
Yeah.
Thank you.
You're welcome. Now you need to collect everything again. It's a Chinese phone you're using?
Yeah.
I used to have one, but now I have another one. It's well, I guess it's mostly produced in China. Okay, I find this interesting. It's a so-called Fairphone. Do you know this? This idea? The idea of the Fairphone is that the whole production process is closely monitored for being fair. That's why it's called the Fairphone. So people working in production, people working in mining, because there are lots of materials inside. For every part of it, the idea is to look at, okay, let's try to be, say, good citizens and make sure that people get a decent pay and good conditions and so on. So that's the Fairphone, and I'm sure it's very different from the conditions that the phone was made, like every other phone. I mean, it's also true for the iPhone and whatever.
Yeah.
Okay. So, well, okay. I guess I'll see you tomorrow.
Yeah. See you.
Okay. Tomorrow is 2 o'clock instead of 3.
Yeah. I know.
Okay. You plan to go to this master seminar later?
Oh, what?
There's a master seminar at 4 o'clock.
Maybe not, because I have a lot of assignments to finish. Yeah. Sorry.
Yeah. Okay. See you tomorrow.
Yeah, see you.
Bye.
Bye.